Today we start working with the first derivative test, which gives us another way to find maximums and minimums. Yay. If we have a graph of some function that looks like this, and let's say that this x value is c and this x value is h. Now let's talk about this for just a minute. Obviously, right here at this point there is a maximum. We know that. And right here at this point there is a minimum. All right? And we've talked about the fact that the slope of the tangent line at those places is equal to 0. But we're going to take a little bit different perspective now, and we're going to talk about what's happening to the slopes of the tangent line to the left of this maximum. What is the slopes of the tangent line to the left? If we were to graph the derivative, what kind of values would they have? Positive values. Very good. And if I came to the right of this maximum value, okay, now what am I putting here? You better put it in your notes. This is the values of f prime. All right? So f prime over here would be negative. And then to the left of this minimum, they're negative. To the right of the minimum, f prime is positive. And that leads us to the first derivative test. The first derivative test says, number one, if f prime changes from positive to negative at C, then f of C is a local max. If the value of the derivative changes from a positive value to a negative value at C, then f of C is a local maximum. All right? Kind of like what we said about velocity, right? Okay, same kind of idea. So that's statement number one. Let's get statement number two. I think you know what statement number two says. If f prime changes from negative to positive at C, then f of C is a min, or a minimum. And it is possible that there's no change in sign. So number three is if there's no change in sign, yeah. And like I said, we're not going to be worried much longer about whether it's local or absolute. We're mostly just going to be finding maxes and mins, okay? And if there's no change in sign, then there's no max or min. Absolute and local maximums and minimums are something that we need to know about and know how to handle, but more often than not, we're not dealing with them. So let's get right to an example. Let's find the local extrema. So remember that fancy word extrema just means we're looking for maximums and minimums. All right? So let's say that my function is x cubed minus 12x minus 5. Well, just like the last couple of days working with extrema, what do you think we need to do first? Find the derivative. You people are doing excellent. So this is an easy derivative. F prime of x is 3x squared minus 12. And just like before, we need to set it equal to 0. So we will set this equal to 0 and solve it. 3x squared minus 12. Add 12 to both sides. So 12 equals 3x squared. We know what this is going to turn out to be. X squared equals 4. And I have two values, positive 2 and negative 2. We were not given an interval on this one, so we're going to work with both of them. Now, the question of this is, what are those? And I know they're critical points, but now we want to use the first derivative test to see if those are a maximum or a minimum. So let's see how we do that. Get to a new page here. The best way, I think, to consider this is with a number line. Here's 0, of course. Our 2 points were at 2 and negative 2. Those were our 2 critical points. Now, didn't we just say that we can look at what happens to the value of the derivative left and right, of these critical points? So all we need to do now is let's find the value of the derivative left and right. Let's do, maybe we should do f prime of negative 3. And if it were me, and I was picking a value to the right of negative 2, I'd use 0.
So we use f prime this time or not?
F prime of 0, because remember, we're comparing, let's go back to our first screen. Remember, we are comparing the values of the derivative left and right. Okay? So, yes, we are going to use the derivative. We'll do f prime of 0, and then we'll do f prime of 3. Okay? So, f prime of x, we said, was 3x squared minus 12. So we will do f prime of negative 3. So that's 3 times negative 3 squared minus 12. So that's going to be 27 minus 12, which is 15. And the most important thing that I need to know is that that's positive, right? So when I am to the left of this negative 2 up here, I'm positive. Now, we could take a wild stab and guess that maybe the next one's going to be negative. So I'm going to use red. F prime of 0 is going to be 3 times 0 squared minus 12. That's easy. It's negative 12. We were right. So there, the value of the derivative is negative. Now we just need to check f prime of positive 3. And isn't it going to be the same thing as what our first one was, because we're just squaring it? F prime of 3 is also going to be 15. So this one is positive. So guess what? We can make our conclusions now. Negative 2, let me get a different color. What is this one? Is that a maximum or a minimum?
Maximum.
It's a maximum because it's switching from positive to negative. So this one is a max. This one is a minimum. Now, if I wanted to finish up my problem, though, those are just the x values, right? Those are the x values where a maximum and minimum occur. It's not the actual maximum value. The actual maximum value occurs when x is negative 2. So I know that it's at negative 2. So if I want to find the maximum value, I need to plug it back into the original function to actually find that exact maximum value. F of negative 2, well, that's going to be negative 2 cubed minus 12 times negative 2 minus 5. That turns out to be 11. So my actual maximum value is negative 2, 11. That is the actual location of the maximum value. Everybody follow that? Just once you find out that negative 2 is the x-coordinate, you just have to plug it back into the original to see what that maximum function value is. And then we do the same thing with the minimum. All right? For the minimum, I would do f of positive 2. I'm just going to tell you what that is. F of positive 2 is negative 21. So your minimum value is positive 2, negative 21. All right? Let's look at a function now that's maybe not as friendly as the first one we did. We'll do another example here. Let's say that my function was x squared minus 3 times e to the x. And we wanted to find our extrema using the first derivative test. So first order of business is finding the derivative, and I'm going to have to use the product rule. Good. So the derivative of the first function is going to be 2x times the second function the way it is, plus the derivative of the second function, which is just e to the x, times the first function the way it is. Now, at this point, what we have is 2x e to the x plus e to the x times x squared minus 3. And we want to set that equal to 0. And right now, everybody's worried and concerned because we don't know what the heck to do with it. And if you leave it that way, the way it looks right now, it is a problem. But what we want to try to do when we're setting stuff equal to 0 is try to get it into a form that we can do something with it. And one way we can do that is to get this thing right here written as a product. Because if I've got something times something equal to 0, then I can split them up. Do you see something that's common to both of these?
An e to the x.
An e to the x. If I pull out an e to the x, then I'm left with 2x plus x squared minus 3. Just factoring out an e to the x. And that is equal to 0. And now we have this written as a product, which means I can use the 0 product property like we do when we're factoring and set e to the x equal to 0 and set this quadratic equal to 0. I'll write it in its normal order. And now we have two separate little problems that we can solve. We'll start with the quadratic. This factors x plus 3 times x minus 1. So I have two values there. Two critical points. X equals negative 3 and x equals positive 1. There's two critical points. Now how about e to the x equal to 0? Well, this is where it helps us to remember our function family. What does the graph of e to the x look like? Doesn't it look like that? Is there ever a place where e to the x equals 0? Remember, there's actually a horizontal asymptote right there. The regular e to the x function never equals 0, so there is nothing here. That one does not exist. But I still have two critical points. So let's work with these two critical points now using the first derivative test. From this point on, it's just like the last problem. Here's 0. I have a critical point over here at -3, and I have a critical point at +1. So we need to check the value of the derivative left and right of those critical points. So looks to me like we would do f prime of -4. We're going to use 0 any chance we get, f prime of 0, and then we're going to do f prime of 2. So this really just boils down to, can I finish the problem analytically correctly? My function, my derivative, we said was e to the x, after I factored out the e to the x, times x squared plus 2x minus 3. So if I'm going to do f prime of -4, that's going to be e to the -4 times 16 minus 8 minus 3. So the part, excuse me, in parentheses is going to be 5. And this thing right here, that's not negative, is it? E to the -4 is not negative. That just means 1 over e to the 4. It is going to be a small number, but it's going to be positive. So all I need to know is that this thing is positive right here. That's all I care about. All right. So this one to the left of -3 is positive. Now we can find f prime of 0. Better draw a line here. F prime of 0 is going to be e to the 0 times 0 plus 0 minus 3. So e to the 0 is 1. Yes, 1 times -3 is -3. This one in here is negative. I think you know what's happening here. When I do f prime of 2, I have e to the 2nd times 4 plus 4 minus 3. That one is also going to be e squared times 5, and that one is also going to be positive. So guess what? We've got all the information we need to say if it's a maximum or a minimum. Once again, this one worked out kind of like the last one. When x equals -3, that's a max. And when x equals 1, that's a minimum. Okay? And then you would plug in those values into the original function, all right, to get the actual y value. Remember, we go back to the original function. So, the original function was x squared minus 3x. Was it 3x? X squared minus 3 times e to the x. So we found out our two values were -3 and 1. So f of -3 is going to be 9 minus 3 times e to the -3. So that would be 6 over e to the 3rd. That's good enough. That's a very exact answer. Even though it's not, we didn't multiply it out with a calculator, that is a very exact answer. And so I would say that my maximum is at -3 and 6 over e cubed. And then my minimum was at 1. So f of 1 is going to be 1 minus 3 times e to the 1. So that's going to be -2e. So my minimum is at 1 -2e. So that's good enough, okay, what we have there. Okay, one more problem just because sometimes people have issues with trig functions. What if I have 1/2 x plus the sine of x, and they ask you to find the extrema from negative 2 pi to positive 2 pi? Okay? Our process is still the same. Just because there's a trig function there, that's nothing to be worried about. We just find the derivative. F prime of x is going to be 1/2 plus the cosine of x. Okay, the derivative of 1/2 x is just 1/2. The derivative of sine is cosine. So we still set it equal to 0. And now what we need to do, this one we're not going to leave it equal to 0. Hopefully you see why. If I subtract 1/2 from both sides, now I've got this expression, where does the cosine of x equal negative 1/2? And this is why I've tried to preach to you about being able to visualize the graph in your head. We're working from negative 2 pi to positive 2 pi. Here's 0. Here's 2 pi. Over here is negative 2 pi. Here's 1. Here's negative 1. Cosine obviously does this. All right. We know this is pi. And then it does this again, doesn't it? And so isn't this negative pi? Right? And so now we have to ask ourselves, where does cosine equal negative 1/2? And those are some of those memorized values with the bow tie that we learned about. Okay? And so obviously, if we're looking at negative values, we know, just to kind of give you an idea, we know that we're looking in this section right here, because those are the places where cosine is negative, right? And if you come back to our all scholars take calculus, okay, then you can pretty quickly figure out the answers to these problems. All right? Because now I just need to fit, I know I'm going to be working over in these two quadrants, because that's where cosine is negative. I need to draw a triangle, right, so that I get the cosine of an angle to equal negative 1/2. Now you know it's got to be a 30, 60, 90 some way, doesn't it? Right? And so cosine is adjacent over hypotenuse. So you have to draw your triangle in such a way that you get negative 1/2. And we're going to stop there for today.